Hello class, this is a video tutorial on trigonometry and the unit circle part 2. This is a continuation of deepening our understanding of trigonometry. Just as a quick overview, in the previous video we learned about the unit circle, how reference angles are made between the initial and terminal side. So the initial side here, terminal side there. And the right angle is formed using the x-axis and the intersection between the terminal side and the unit circle. So that triangle there is what we are generating. Here's a neater version. And we saw that using the classical trig ratios, SOHCAHTOA, we found that sine theta is just y because it's opposite over hypotenuse. Y over 1 is just y. Cosine of theta is the adjacent over hypotenuse, which is x over 1, that's just x. And we saw that tan of theta is opposite over adjacent, so we take y and we divide it by the x value. And in the previous videos we saw the operation of trig, of how it works in the calculator, and how you could possibly do it by hand if you were patient enough. So I'll demonstrate it one more time. So sine of 37 means we draw the unit circle, we find an angle of 37 degrees. Let's say that will be approximately, that's 45. Let's say it's about here, I guess. Yep. So from there we draw the triangle. And we're now going to find the length of the opposite from the angle of 37 degrees. So what is this length here? To me that looks about 0.5. 1, 2, 3, 4, 5, 6. Oh, okay. It's divided into fifths, so I'd say that's about 0.6. So sine 37 calculated by hand is 0.6. And if we calculate this using a calculator, sine of 37 is 0.60181, etc. Okay, well, hopefully that jogged your memory. But now the question comes up now is, but what about triangles larger than what can fit inside the unit circle? How do these relate to what we now know? Again, by understanding how these larger circles fit into the unit circle, we'll better understand, spelled wrong, we'll better understand the reasoning for the methods used to calculate missing sides of a right angle triangle. Okay, through the properties of similar figures, all right angle triangles are similar to a particular right angle triangle found inside the unit circle. So in this case, clearly we have a triangle whose hypotenuse is 3, and that couldn't possibly fit inside the unit circle, which has a radius of 1. But we could try. So for example, here's my unit circle, radius of 1, not drawn to scale, and I'm going to try and fit this inside the unit circle. So it'll be about like that. It actually would be a lot larger if we think about it. But there we go. Okay, so that there is this big triangle that we fit inside the smaller triangle. But can you see that we could actually still draw that triangle inside with the same angle of 53? So we can draw a small triangle like this, while the large angle is still allowed to exist outside of it. And from here, we could actually separate both of them into two smaller triangles. So we have one like this. There we are. That's 53. We don't know what this length is, but we know it's a length of y. And this length here is a length of x. The green triangle is a larger one, so it's actually, we'll just copy it here actually, out like this. This also has a length of y that we don't know, and this one, length of x that we don't know, but we do know that the radius of this is 3, the hypotenuse as well, sorry, and the radius of this one is 1. What do you notice about these two triangles? Well, they're actually the same triangle, but one is just 3 times as larger. It's an enlargement. So this unit circle triangle has been enlarged to become the triangle that we've been given in the question. But actually we do know what this length is, because that corresponds to that y value in the unit circle. In this case, from looking at it, it looks to be about 53 is not drawn accurately. 53 would actually be about here, but I hope you understand the point that sine, well, this length of here, this y value here, is sine of 53. Okay, so that's sine of 53. 0.798, so let's just say 0.8. So this y value is actually 0.8, and this coordinate here is actually something 0.8. Now I want you to consider that from 1 it has become 3. Can you see how that's being multiplied by a factor of 3? So it's enlarged by times 3. Well, if the hypotenuse has been enlarged by a factor of 3, shouldn't this also be enlarged by a factor of 3? Well, 0.8, we'll multiply that by 3. That will give us, well, this one will be equal to 2.4. Okay. Well, let's do the same process for this x value. Now remember, this x value here corresponds to the coordinate of this one. Well, we can find what that is. Sine of 53, oh sorry, that's cosine of 53, sorry, cos of 53 to the adjacent side is 0.6018. So this is 602, let's say. Well, in the same process, we've taken 1 to become 3, so it's been enlarged by a factor of 3. We're going to do the same thing, so 0.602, and multiply that by 3 as well. So 0.602 times 3 times 3 is actually 1.806. But now let's compare what we just did to the regular process that we would normally do. So for example, if we wanted to find, let's draw this triangle again. If we wanted to find the triangle that we drew, that's 53 degrees. 3 is the hypotenuse, and this one here is y. If we wanted to find that, we would say sine of 53 equals opposite y over 3. And if we multiply sine 53 by 3, we can get, so 3 sine 53 equals y. But isn't this the exact same process that we did here? We found the value of sine 53 and enlarged it by a factor of 3 to find this value here. So now let's see how well this compares if we just type it completely. 3 sine 53, 2.395. So y is equal to 2.395, which is very close to what we estimated to be 2.4. So I hope that gave you an insight into what's actually happening when we do these processes of finding missing sides. I'll be doing 2 more examples here in the next video. Hope to see you then.